Okay, Assalamualaikum and good morning. Okay, today I'm going to explain to you this example on 3D equilibrium problem. Okay, in this example, we have a system where we have a mass hanging, okay, 30 kilogram, and then at the same point of the cable hanging the mass, the weight, okay, we have three forces, T1, T2 and T3, to hold the mass in equilibrium. So in this problem, we are given the mass is 30 kg and it is supported by the three forces, T1, T2 and T3, and we are asked to find T1, T2 and T3 in order to maintain the equilibrium of the system. And we are given T1 is in YZ plane. Okay, T1 is in YZ plane. So we have to use that information. So we can start with finding the T1 component of force, vector force T1. Okay, as we are given X or YZ plane, T1 is only in YZ plane, meaning that it will only have the Y and Z component, okay, for T1. So you have 0 X component, and then for Y component, okay, we can just use T1 and the angle given 30 degree, okay, from the y-axis. So you can just take, okay, T1 cos 30, okay, because 30 degree angle is, okay, sweeping that to y-axis, y component. So T1 cos 30 J, and then for the Z component, okay, we have just need to take T1, okay, away from 30 degree angle. So we have to use sine 30, T1 sine 30, and the direction is in the opposite and the negative Z direction. So negative T1 sine 30 K, okay, for the Z component. So that is for T1, and then for T2, okay, looking at the vector force given, T2 is acting on XZ plane, okay, 20 degree from x-axis. Okay, so we should know that the T2 vector force will only have X component and Z component. Okay, X component and Z component. Okay, we have to find the X component first. You can use T2, okay, 20 degree angle, sweeping that 20 degree angle. Okay, you have T2 cos 20 degree, T2 cos 20 degree I for X component, and 0 Y component, okay, because it is acting only and in X and Z plane. Okay, so 0 Y component, and then for Z component, okay, we are taking that T2 away from 20 degree, okay, so using T2 sine 20, T2 sine 20 degree K, okay, in the positive direction for Z component. Okay, and then we move to T3. You are given that vector force T3, okay, and you are given the angle from x-axis, y-axis and z-axis. Okay, x-axis the theta 3x 115.3, and from y-axis you have theta 3y 30 degree, and from z-axis is given theta 3z 75 degree. Okay, from first angle method, okay, we can just apply the formula for the vector force in terms of IJK. Okay, you can, for T3, for X component, okay, we just use T3 cos theta 3x cos 115.3. For y component, it is just T3 cos theta 3y, okay, 30 degree J plus T3 cos 75 degree K, 75 degree. Okay, so this is the vector force for T3 in terms of IJK. Okay, and then the last force acting is due to the mass. Okay, and if we write it as a W, okay, the force W, which is the weight, okay, of that mass, equal to, you know, the formula for weight, which is mg, and then it is acting only in the negative y direction, okay, negative y direction. So we have only one component in the negative y component. Okay, so you have 0I, and then mg, mass is 30, g is 9.81. Okay, you have 294.3 J and 0K. Okay, so this is the all the vector forces, okay, acting on the system to maintain the system in equilibrium, okay, in terms of IJK component. Okay, so okay, from this vector force component, we can create a table, okay, and then we can use the equilibrium formula, which is summation of forces in x component will be equal to 0, and then the summation of forces in y component equal to 0, and summation of forces, okay, in z component equal to 0. Okay, we will look further in this problem. Okay, we will proceed with the table after this. Okay, this is the table, okay, that we can form, okay, from the four forces that we have before, T1, T2, T3 and W. Okay, we can, okay, collect all the, this is the, okay, component for T1 0, and then 0.866 T1 for J component, and negative 0.5 T1. Okay, for T2, this is the I component, J component, K component. Okay, and the T3 we have negative 0.4274 T3, okay, 0.866 T3, and 0.2588 T3. Okay, and this is for vector force W. We have the negative y direction. Okay, we have negative 294.3. Okay, and then what we can do is that, okay, to sum all the I component for T1, T2, T3 and W equal to 0. Okay, because we have, this is the summation of fx for I component, this is summation of J component equal to 0, and summation of K component equal to 0. Okay, so okay, from summation of L component, okay, summation of this component, we can get the relationship T2 with T3. Okay, you have 0.9397 T2, okay, equal to 0.4274 T3. Okay. Okay, now we will continue with the equation of I component, J component and the K component. Okay, from the table before, okay, we can gather all the I component. Okay, we gather all the I component, you will have 0.9397 T2 minus 0.42743 T3 equal to 0. Okay, for I component, total summation of fx equal to 0. Then you can have the first relationship, T2 equal to 0.54584 T3, and then okay, we move into J component. Okay, summation of Fy equal to 0. Collect all the J component, 0.8661 plus 0.866 T3 minus 294.3 equal to 0. And then you can have the second relation equation, T1 is equal to minus T3 plus 339.8. Okay, so we just give it equation number 2, and then we collect the K component. The K component, okay, summation of Fy equal to 0. You have negative 0.5 T1 plus 0.342 T2 plus 0.2588 T3, okay, equal to 0. And then what we can do is we apply the substitution. Okay, we can apply, we can substitute equation 1 and 2 into equation 3. Okay, so we can just substitute T1, okay, negative 0.5 T1. T1 is equal to minus T3 plus 339.8. Okay, and then plus 0.342 T2. This is T2 in terms of T3 plus 0.2588 T3 equal to 0. So we have, okay, the equation in terms of T3, okay, at this equation, okay. For example, this is, we mentioned equation 4. Okay, so now with equation 4, we should be able to solve for T3. Okay, we should able to solve for T3. Okay, and then we will have, okay, okay, we will have, okay, quickly just write, okay, from this equation we can solve. Okay, we will get T3 equal to 185.8 Newton. Okay, once we get T3, okay, from solving from equation number 4, okay, then we can, okay, we can solve for T2. Okay, just substitute the value of T3. Okay, we got T2 equal to, okay, 0.4274 times 185.8. Okay, will give you, okay, will give you T2 84.5 Newton. Okay, you get your T2. Okay, and then we can move into, okay, the next equation. We can solve for T1. Okay, T1 equation 2. Okay, so T1, okay, solve for T1, just minus 3, minus T3, sorry, minus T3 185.8 Newton plus 339 plus 339.8. Okay, give you, okay, you will get T3 equal, T1 equal to 154 Newton. Okay, so there you go. Okay, so for this 3D particle for equilibrium problem, okay, we can solve, okay, by getting the vector form in terms of ijk component, and then we can collect the I component, okay, j component and k component, and we can create, okay, the substitution, okay, in order to solve for the unknown. Okay, in this example, okay, we can solve T3 first, okay, by using the substitution, okay, the value for the unknown. Next one, we managed to solve for T3, okay, you get your T3 value, then you can apply to the previous relationship, T2 equal to, okay, the value of the T3, okay, the unknown that we have found. Okay, so we just continue, find the T2, and then once you get your T2 value, you can continue find your T1 using the answer that we have. Okay, so we can get the answer using the substitution method, solving the simultaneous equation. Okay, so that's all for this example. Thank you very much. We'll see you again.